All right, guys, welcome back. Unit 6 review is on random variables. In this video, we're going to go over kind of how you do some of the basic calculations as well as the different types of random variables you are likely to see. The main types, you might see like a discrete random variable, a normal random variable. We did with binomial random variables. And geometric. So we're gonna go through each of those. We're gonna talk about how you can calculate the means and standard deviations of several of them, and how we deal with their variances as well. So let's jump right in. Learning target 1. Use the probability distribution of a discrete random variable to calculate the probability of an event. Okay, so it says below is a probability distribution for a discrete random variable C. Let C represent the number of cats a randomly selected Fairbanks North Starborough English teacher owns. Your options are C equals 0, C equals 1, 2, 3, 4, and so 4 would be the maximum. It says calculate the probability of an event. Our event is that one randomly selected Fairbanks North Starborough English teacher owns less than 3 cats. Well, to figure that out, we would add up the probability that C is equal to 0, because it's discrete, we can go through each of these individually, plus the probability that C equals 1, plus the probability that C equals 2. We don't do 3 because it's not equal to. If it was, we would. Okay, and so that's going to be 0.1 plus C equals 1, 0.2 plus 0.4, which will give us a 0.7 probability, or a 70% chance. So there's a 70% chance that the randomly selected person that we choose has less than 3 cats. Perfect. Keep on trucking. Okay, you might also be asked to make a histogram of the discrete random variable and describe its shape. So for that, let's go ahead and just figure out the strategy here. I like so you put your probability on the y-axis and your different discrete values on the horizontal axis. So let's go ahead and draw our vertical and horizontal axes and throw on there 0, 1, 2, 3, 4. And then for here, we'll go up 1, 2, 3, 4, and 5. We'll go by 0.1. We don't need to go higher than 0.5 because there's no probability or no bar of our histogram is going to go that high. Okay, cool. So when we're drawing our histogram, we go through. There's 2 ways that you can do it. You can make it like a histogram, or there's several ways, but you can have it fall to the bucket to the right. So like 0 is to the right. That's a little weird. I think for discrete random variables, it's easier to just come through at 0.1, like right here, and then put it centered. I know that's not technically what you're supposed to do with a histogram, but it works for this, okay? And that's not quite in the middle, but let's try that one more time. You kind of want to get it in the middle if you can. There we go. Okay, and then you want the areas of the rectangles to appear the same width so that you can kind of compare, and area-wise it's representative of what you see. Okay, so let's see here. 0.2 for the variable 1. I'm going to come up here to 0.2, come directly across, come down and down. 0.4 for 2, come up to 0.4, come across, and let's just come directly up so we keep it centered. Not my finest work on that one. We're going to keep rolling. And then 3 and 4 are both 0.15 probability. I'm going to go out past 4 because the tick marks are centered. Come down and cross it over. So there we have our histogram of the probability distribution. I would describe the shape of this histogram as roughly symmetric. You could argue that it might be skewed, but based on what we see, I would say this is roughly symmetric. Okay. Let's go ahead and move on. Keep cruising. Learning target 3. Calculate, interpret the mean or expected value of a discrete random variable. And I'm actually going to take this time to pull up. Let's take a look here. They released a new-ish formula sheet for the 2020 stats exam. And I'm going to show you where this is. So for a discrete random variable, that's the first thing that we see here for probability distributions, and it says the mean, or E of x is the expected value of that variable, is equal to the sum of those values times their probabilities. So that's our mean. So that's how we're going to start. The way that we say that is we say mu of c, or the expected value of c. Can we see that okay in our... Let's take a look here. It's a little hidden. It's okay. All right, back. Mu of c, or the expected value of c, is equal to the sum of all of the c sub i's times the probabilities of all of those c sub i's. So what is that going to be equal to? That is going to be 0 times 0.1 plus 1 times 0.2 plus 2 times 0.4 plus 3 times 0.15 plus 4 times 0.15. Okay, and I'll let you check my math there, make sure we get the same thing. Let me see what I got for an answer. I ran through this the first time. All right, well, 0 times 0.1 is 0, so that's easy. Plus that is going to be 0.2. That is going to be plus 0.8. That is going to be times 3. Plus 0.45 plus 0.60. And when you add all those up, you get, what do we get? 2.05. So the expected value of C is 2.05 cats. We can expect the randomly selected English teacher on average to be somewhere close or centered around 2.05 cats. All right, super. We've done the mean. Let's move on to our next learning target. The next learning target says calculate, interpret the standard deviation of a discrete random variable. Okay. Well, if we go to here, it says the standard deviation of the statistic is equal to, so the standard deviation is equal to the square root of this, and you have this big formula. That's just fine, and we can use that. That's okay. We'll use that. So we'll say the standard deviation, I'll start over here, the standard deviation of C is equal to the square root of the sum of the C sub i's minus mu sub C. So minus the mean that we just calculated squared times the probability of all of those C sub i's. I think I got that right. Let's double check. Yep, just replace x, we're good to go. All right, so this is the standard deviation of our statistic. Let's see. Yeah, let's go. Let's do this thing. We got this. No problem. All right, so basically you do all this for each of the values of c, and then you add them all up when you're done. And take the square root. Square root's the last, follow the order of operations. So I'm going to write, this is the square root of, and I know this is cheating, but I'm going to make a very, very large square root here. This is going to be the square root of, just remember that there's a giant square root. That is 0 minus 2.05 squared times 0.1 plus, next one, 1 minus 2.05 squared times 0.2. Okay, so we've done the first two. We keep going. 2 minus 2.05 squared times 0.4 plus 3 minus 2.05 squared times 0.15. Try that one more time. It's better, and I'll put a plus there, and plus 4 times, if you're doing this on the AP exam, I'd maybe try and put it all on one line, if you could. 4 minus 2.05 squared times 0.15. Sweet. All right, so we've got the sum, we've plugged in all the things times their probabilities, and now you just got to sit and do math, and you end up getting the square root of a lot of numbers added together. It ends up being like 0.42025. If you're trying to be accurate, I would just kind of keep these values stored in your calculator if you can. 0. And my handwriting is bad. 2205. Maybe I should check that one. 2205. Plus, the third term is hardly anything because 2 and 2.05 are so close. You end up with 0.001 plus 0.13537 plus another large one, 0.57013. 57037. Look at that. So we add all those up and we take the square root, and we'll get the standard deviation of C is equal to the square root of 1.3475, which is 1.161. Sweet. Here we go. So we've got the standard deviation of our discrete random variable. By the way, remember it's called discrete because there are a countable number of values. The opposite of discrete, or the other type of data you can have, is continuous. Continuous is there's an infinite number of values, and that would be like a normal distribution. Is on a continuous scale, or measuring something like temperature or race times. Here we're measuring something countable, cats, so we're using a discrete random variable. And our units here are cats. Okay, so what does this mean in terms of the context of the question? It means that we can expect random selections of number of cats owned by English teachers. Whoa. to vary from the mean of 2.05 cats by about 1.161 cats on average. Sweet. That's what it means. So it means basically if we were to randomly select from this probability distribution, we can expect that it's plausible that we're going to be seeing something between 1.161, around 161 cats larger than the mean or smaller than the mean, usually. So it's going to vary somewhere in that range about. Okay, in blue, switching colors. Describe the effect of adding or subtracting a constant or multiplying or dividing by a constant on the probability distribution of a random variable. All right, before we start this this whole thing, one thing you need to remember, if you look back at when we talked about transforming a distribution, adding and subtracting a number or a constant to a random variable, like we give every English teacher in the Fairbanks North Starborough School District 2 cats. Well, you're adding a constant to everybody. How does that affect our distribution? Adding or subtracting A will result in shifting. Let me make this large. Will result in a shift in the mean by A. So if you're subtracting, it will go lower. So let's say if A is 5, you can subtract 5 to the mean. If you're adding 5, you add 5 to the mean. The variability, aka the standard deviation, the range, everything else stays the same. And the shape stays the same. Cool. How about multiplying or dividing by some letter? We'll say D. Okay. That looks too much like A. How about B? Okay. If you're multiplying by B, this typically is going to scale or stretch or shrink by a factor of B. Okay, so if your mean is 0, it's not going to stretch or shrink anything. But if, for example, you're converting units, then it's going to be changing your it's going to be changing your mean. Stretch or shrink the mean of C by a factor of B. Okay, great. Variability is going to, you would basically times or divide by B. So the range and the shape will be the same. Okay, so basically the variability here is going to, you multiply, and when I say variability, I mean standard deviation, range, interquartile range. Okay, so you're scaling by B, so you would do B times the range to find the new range, or B times the standard deviation to find the new standard deviation. Hopefully that rings some bells there. Let K represent the total amount a randomly selected English teacher spends on cats each month to take care of them. If each cat costs $35. Find the mean and standard deviation of K. All right, let's go ahead and get started. So this is how we show our work for these. The mean of the random variable k is equal to the mean of, so basically you need to know that the random variable k, basically if a cat costs each cat costs $35 to take care of a month, then the amount that you're paying to take care of cats is 35 times the number of cats that you have. But the number of cats you have follows the same probability distribution, or follows, so basically k is dependent upon c. So we would say this is equal to 35 times c. So you can see, if we go back to where we calculated our mean, if I were to take all of these things and multiply each term by 35, well, I could just take the result and I could factor that out and take the result. Because basically you're multiplying each of these things by 35, which means each of these things you're going to multiply by 35, which means you'll be able to factor out a 35 and multiply at the end. Hopefully that made sense. So what we can do here is, when you multiply, you have a random variable situation like this, you would say this is equal to 35 times the mean of c, which is 35, and we know the mean of c is 2.05, and 35 times 2.05 is 71.75. So the expected amount that you would think a randomly selected teacher would pay per month to care for their cats is $71.75, and that is mu sub k, the mean or expected value, 71.75. Okay, let's think about the standard deviation. The standard deviation of k is the same thing. You can multiply the standard deviation of k. This follows the same rule. So you'll just do, it's the standard deviation of 35c, which is 35 times the standard deviation of c, which is 35 times 1.161, or 40.635. So basically, on average, we can expect the randomly selected teacher to vary by about $40 from the mean of 71.75, based on the amount of money it costs to take care of cats. Sweet. All right, let's keep going. We're doing good, making good time, I think. Calculate the mean and standard deviation of the sum or difference. Sum or difference of random variables. Let D be a discrete random variable representing the number of dogs a randomly selected English teacher in the Fairbanks North Star Borough School District owns. D has mean of 1.6 and a standard deviation of 2.3. Notice that we don't actually have to see the distribution here. The question is, assume each dog costs $55 per month to take care of. And we're going to let A be equal to the total cost a randomly selected English teacher pays per month for their cats and dogs. Together, find the mean and standard deviation of A. Okay, there's a couple rules you got to get down here before we get started. What color am I in? Blue. The first rule is, I might need to move these. I think I do. Oh yeah. Yeah, we're setting this up nice. This will be good. All right. So the first is, if you are doing a sum or a difference, the mean of a sum, x plus y, is equal to the sum of the means. You got to have that down. And the mean of a difference is equal to the difference in those means. Great. How about standard deviation? Well, actually, the rule doesn't have to do with standard deviation. It has to do with the variance. But remember that the variance, so if this is the standard deviation, the standard deviation, variance is sigma squared. They both have their own statistical name. And the rule has to do with the variances. So it turns out that when you're adding two random variables, so if you do sigma squared of x plus y, that is equal to sigma squared of x plus sigma squared of y. Super. Okay, and if you do a difference, sigma squared of x minus y, I don't know, I think so. It's the same thing. So this is where people get confused. They think that you have to change this to a minus because that's a minus, and you don't. You're still adding the variation. Yep. So make sure these are both positive when you're doing these, and these ones change based on the sign that's happening. All right, now let's look at this problem. So we want to know how much it costs to basically for a randomly selected English teacher to take care of their cats and dogs, and we're trying to find the mean and standard deviation. Yikes. Okay, so the mean, we'll call this A. The mean or expected value of A is equal to the mean of, and here we do, it's really A will be equal to $35 times the number of cats plus $55 times the number of dogs. So we do mu of A is equal to the mu of 35C plus 55D, which is equal to the mean of 35C plus the mean of 55D. Okay, when we're adding, the mean of a sum is equal to the sum of their means, we said before. Okay, so we already know what this is, so that's going to be 35 times the mean of C plus, this is going to be 55 times the mean of D. Okay, and we know the mean of C is 2.05, so we do, and we know that that's actually 7175, we did that last time, and this is plus 55 times, it was 7175, right? The mean, where am I? Oh yeah, mean, okay, 7175, there it is. Okay, perfect. Plus 55 times the average number of dogs. The average number of dogs is 1.6. So as we continue down, let's keep on cruising. We add those together. Double check my notes here. Make sure I got the right number. Yeah, looks good. All right, so 7175 plus 88, which will give us a final expected value for adding these this linear combination of random variables of $159.75. So that means on average, it is going to cost a randomly selected English teacher in the Fairbanks North Star Borough School District $159.75 to take care of their cats and dogs. Boy, that's a mouthful. We're gonna do one more because it says find the mean and standard deviation. All right, this is where it gets fun. I know you guys believe me when I say fun, right? All right, let's think about this. All right, so in this case, we know that, I lost my notes, hold on. Yeah, we know that A is equal to 35C plus 55D, and A is the amount that you're gonna pay per month, right? We just went over that kind of. Well, these are the two random variables that we're adding. So what we're doing is we're finding the variance. We're going to do it in terms of the variance, and then when we get down to the variance, you can square root. So basically, right here, the standard deviation is equal to the square root of the variance. We're allowed to do that. So, and the standard deviation, or the variance, is the standard deviation squared. So we're doing sigma squared of A, or the variance of our random variable A, is equal to, we're going to do the variance of 35C plus 55D, because that's what A is equal to, just using kind of the property of substitution there. And we know from the last slide that when you add or subtract two random variables, you can split those random variables up and you add their variances. So we can know the variance of 35C, and we can add up the variance of 55D. Okay, the variance of 35C we have not done, but we do know I think the standard deviation of, we know it of K, we don't know it of, interesting. Okay, that's all right. We know the standard deviation of 35C is 40.635. Okay, interesting. So let's go back, 40.635, or we could round up to 40.64, I guess. All right, so if we're going to do that right now, we're going to do it the way that I'm going to do it, or I would do it, and then we'll come back and check and figure out. We can just do 40.64 squared, or we can know that this is the variance of that value, which is equal to 35 times the variance of C squared plus 55 times the standard deviation of C squared plus 55 times the standard deviation of D squared. Well, we already did this calculation. 35, let's double check and make sure that makes sense. 35 times the standard deviation of C, yeah, you're going to end up with 35 times 1.161, which is your 40.64. Okay, so this is going to end up being 40.64. So we kind of did that work twice, but that's okay. And then this will be 55 times D, the standard deviation of D, which was given to you on the last slide as, in the green paragraph, 2.3. So we plug 2.3 in here, and then we follow order of operations to get our answer. We're going to get some big numbers, but that's okay. 35 times 1.61 squared is 1,651.20, and this one is plus, you're probably thinking this is way too big. Don't worry, it scales down. 16,002.25. Now remember, this is the variance of A. We don't have the standard deviation yet. So we add these two together, and you get 17,653.45 for the variance of A. So that means the standard deviation of A is just the square root of that value. Which is $132.87. Let's see if that number makes sense in the context of the question. We can expect on average, for the average person basically, to pay around $159, or average English teacher, $159.75 each month to take care of their cats and dogs. Well, they could have no cats and they could have no dogs, so varying by 132 is a plausible amount to vary by for this, and you could have more than that, so that's a pretty decent answer. If you typically vary by about 132 from that value, you're not going, you're not going into the negatives consistently, so that this value is plausible. Whew, that was a lot. It's this jump that's hard for people, going from here to here. And it has to do with the fact that we are squaring the standard deviation of 35C. And in relation to the standard deviation of C, it's just 35 times bigger. So this 35 ends up getting squared in this process. You could do, you could do this to the second and this to the second, and you'd still get the same value. But it's this jump that is tough for me, and I have to kind of remind myself why that works. And it just has to do with this rule right here. Which rule? This rule right here. You multiply the variability, the standard deviation, times the value you're multiplying that random variable by. Okay, let's keep going. Probability distribution of a continuous random variable to calculate the probability of an event. Okay. This one says when Mr. Slagle speed runs level 1 of Mega Man, his time is normally distributed with mean 220 seconds and standard deviation 25 seconds. What's the probability that he finishes the level in 250 seconds or longer? So, well, if you look here, basically, we know it's normally, so I said it's normally distributed. So what you're able to do here is kind of use that Z table to show your work. So you find your Z critical value here. Let's grab where's blue? We got our Z critical value. And remember the equation for the Z critical value. So our Z is going to be our observed, the one that we're checking, minus the mean divided by the standard deviation. That's usually what we do. And so we're concerned about where 250 lies, basically. The probability that he finished the level in 250 seconds or longer. So that's the boundary of where we satisfy, this event, so to speak. So it's 250 minus the mean of 220 divided by the standard deviation of 25. So that is equal to 30 divided by 25, which is 1.2. Super. So what we're doing is we're really, if we look at the normal curve, I'm not sure if this is visible or not. I don't think, well, I'm going to draw it over to the left a little bit. If we look at the normal curve, basically, here, I'll draw it up here, sort of out of the way. We're looking at, the standard normal curve centered on 0. With each step is 1 standard deviation. So we're looking, if this is 1, remember the first standard deviation is always where kind of the inflection changes on this curve. We're looking at the area under the curve about right over here. But if you look in your updated table and you go to your standard normal graph, it reads to the left, and we're looking for area to the right. So the way that we do that, the way that we write and show that is we say the probability, we're looking for the probability that Z is greater than or equal to 1.2. Well, that is just going to be 1 minus the probability that Z is less than 1.2. Okay, so we know that if we do 1 minus this area, we'll get that area, the desired area. We still want this area, but to do that, we're finding the white area there. So less than 1.2, we can go to our table and take a look. Let's make this large. Okay, that's negative. We don't want less than negative 1.2 because that would be over here. We're looking to the right of the mean. 1.20 is 0.8849. So we do 1 minus 0.8849 to get a final answer of probability of 0.1151. So there's an roughly 11.5% 50% chance that it'll take me 250 seconds or longer on any given attempted run of the first level. I made this data up. I don't think I'm even that good. It'd probably take me a lot longer. Hate to spill the beans. But yeah. Okay, cool. I think we're feeling good. If there's something else I was going to say. Oh well. Go to the next one, I suppose. Man, what was I going to forget? It's late. Okay. Oh yeah. Golly. You can also use normal CDF here because it's a normal distribution. So if you do normal CDF, remember the way that you write that is lower equals, and you can do it with these values if you want, or the standardized values. I think doing it with, unless it's asking you to show your work, in which case you'd want to do this, but normal CDF lower equals, let's do 250, upper equals 10,000, mean is equal to 220, comma, standard deviation is equal to 25. And that should give you the same result. So that's the other way to fill that out. Okay, find probabilities involving the sum or difference of independent normal random variables. His time for level 2, so my time for level 2 is also normally distributed with a mean of 190 seconds and standard deviation of 19 seconds. How much faster is he on level 2 than level 1 on average? So we're going to call this new random variable d. It's going to be the difference in the times. I will call we'll let x represent a time from level 1, and y represent level 2. So how much faster is he on level 2 than level 1? So to do that, we are going to do d equals x, we'll keep the answers positive, minus y. So that means that a positive value means that I am faster on level 2, and a negative value means I'm slower on level 2, which is a possibility. Okay, so it says how much faster is he on average than level 2? Well, what is that? That is the mean, the expected value of d, which is the mean of x minus y, which, hey, we already went over this. That's just the mean of x minus the mean of y, which should be 220 minus 190. So the average of our random variable d is 30 seconds. So you can expect, if I ran level 1 and level 2 and how I did in level 1 was independent of level 2, it would be about 30 seconds. Okay, what is the probability that he is 40 or more seconds faster on any given speed run of these two levels? Okay, 40 seconds faster would mean, what is the probability? We're trying to find the probability that d is, boy, I did not do the right thing in my notes. That's okay, we're gonna roll. Probability that d is greater than 40. So to do this, we are actually gonna need to find the probability that c is greater than 40 minus 30 divided by, we don't know the standard deviation of d, so we're going to have to do that, and I think it's going to take a little bit of work. So we know that whenever we're adding and subtracting, think about the variables, think about the variance. the variance of D is equal to the variance of X plus the variance of Y. And remember, it's always plus for the variance when your variances, no matter whether you're adding or subtracting those variables, which is equal to 25 squared plus 19 squared. Anyways, when you boil this all down, you end up with, let's see, 625 plus 361, which is a standard deviation of D equal to 31.4 seconds. And this is also a believable value because it is possible that on level 1 I complete it faster than level 2. So it's possible for basically the standard deviation and the mean to be close. That's where I'm pulling that from. So down here we are going to divide by 31.4. Okay, and we'll end up with finding the probability that Z, this is our standardized value, and since these are independent random variables, we can subtract them. And you get 10 divided by 31.4. Did not do this the first run through, so hopefully we get the same answer because it's going to be on YouTube. It should be 10 divided by 31.4. which is a Z critical value of 0.318. Okay, so we're looking for the area greater than 0.318, which is 1 minus the probability, because Z reads to the left, of 0.318. And the equals actually doesn't really matter, because the probability of any given value is happening is 0. So less than 0.318. 0.31 is basically, or we'll round up to 3.2. 3.2 we'll say point, or we'll go maybe just a little, oh, it's pretty close. I'm going to say 0.625. That's what I'm going to go with. 0.625 seems reasonable to me. Yeah, 0.625, rounding up. Equals 1 minus 0.625, which is equal to 0.375. Great, we found it. The probability that the difference is greater than 40 seconds is 37.5%. Wouldn't that be wonderful? All right, let's keep moving. Okay, now we're moving on to binomial random variables here. Determine the conditions for binomial setting. Remember, for binomial, you need to check that it's a binary. The example that we did in class was the free throw scenario, where the guy basically, they were down by 2 and he got fouled on a 3-pointer, and so he got 3 shots and had the chance to basically make 1 and lose, make 2 and tie, or make 3 and win, and he could have done that. Okay, so binary. Binary means there is only success and failure in each attempt within the binomial situation. So like in basketball, you can only make the basket or you can miss, right? There's no in between. You want to know that the trials basically are independent of each other. So the probability of one attempt doesn't change the probability of the next. So you could do like coin flips should be 50% every single time. You flip one coin, the next flip isn't dependent. That there is a fixed So the number of trials is fixed. That's what it says. Number of trials is fixed is what that stands for. Is to determine whether or not it's binomial. And the last one is each trial has the same probability. Each trial has the same probability. Okay, let's look at situation 1. Put the names of all the students in your statistics class in a hat. Mix up the names and draw out 4 without looking. Let X be the number whose last names have more than 6 letters. Okay. Can there either be a success or failure? Yeah. You're only going to have people that have 7 or more letters in their last name. A success looks like you have more than 7, you have 7 or more letters. A failure looks like you have 6 or less. So yeah, we have a binary response. And when you're showing, guys, when you are arguing whether or not if this is on there, don't put a B and put a check mark. I'm running out of room. I don't think you want to see me write a whole heck of a lot. I'm trying to walk you through the logic. You might want to say, yeah, we have binary we have binary ways to respond to the trial. A success looks like this. A failure looks like that. Okay, are they independent of each other? Let's think about that. When I select the first person out of that, because it's not, when you're grabbing 4, is who you select on it, when you pull 1 out, is that changing the probability that you get selected on the second attempt? Yes. So you are pulling out 4, but you can really think about it as one at a time. So are they independent of each other? The answer is no. So we can actually stop right there. The number of trials is fixed. That's 4. And they don't all have the same probability because they're not independent of each other. So this is how I would say that. So you'd say since sampling is being done without replacement, the selections were not independent of each other. Now, if you had put them back in the hat, it would be a different case. Okay? Next one. 72% chance. There's a 72% chance that Mrs. Slagle will laugh at Mr. Slagle's jokes. If he tells 7 jokes spaced out over a time. Nice. That was opportunely timed. If he tells 7 jokes spaced out over time, let X be the number of jokes she laughs at from this sample of 7. Let's take a look. Binary response. Yeah, a success looks like a laugh. Boy, this is getting real small. I'm going to zoom in and go down. We're going to check bin. Success looks like a laugh. A failure looks like a stern glare. That's no laugh. Easy. Okay, are they independent of each other? Yeah, I think if I'm cracking jokes left and right, I might, if I get the first one to work, she might be more likely to laugh on the second one. But because I said these jokes are spaced out over time, I think you can assume that they're independent of each other. So you say since there is a delay between jokes, yada, yada, yada. Okay, bins, number of trials. Is the number of trials fixed? Yes. There are 7 jokes being told. Okay, and the last one is the same probability. Do they have the same probability? Yes, 72% on each trial. Okay, and let's take a look. Let me zoom out. So is this is not binomial up here. This is not a binomial setting. This one is binomial. Great. Fantastic. Let's keep going. Calculate and interpret probabilities involving binomial distributions. What's the probability that she laughs at exactly 6 jokes? Well, that is the probability. Do I have a name for my random variable here? We'll call it J. The probability J is the number of jokes she laughs at. It is not the number of jokes she laughs at out of 7. I'm sorry. Yeah, it is. It is the number. Yeah, that's right. Sorry. J is equal to the number of jokes Miss Slagle laughs at out of 7. So what's the probability that J is equal to 6? Well, there's ways to think about this. There are many ways to think about this question, right? You could think, well, yes, she has to laugh at 6 jokes. So if you have 1, 2, 3, 4, 5, this is why this is a nightmare. Don't try and do this by hand, because that could look like 1, 1, 1, 1, 1, 1, 0. Could look like 1, 1. Like if a 1 represents a laugh and a 0 that represents not a laugh. Could look like, there's that option. There's this option, and so you can continue and make all these, and it's just going to take forever. So a faster way to think about this, so basically you think about in each slot has a probability, right? She's laughing at 6 jokes, that means they all have 0.72. And we got to figure out how many different ways there are. So you could see that 0 probably moving to the left in that chart as we were to continue to write down and do those steps. But the way that you use the binomial formula that is on your equation sheet that I'll pull up for you for a binomial random variable, which is somewhere, here it is. The probability that your binomial random variable is equal to some value x, where n is the total number of trials, the fixed number, and then the number that you observe. So it's going to be n is going to be 7, x is going to be 6. So she's going to laugh at 6, and then you do 1 minus the probability. So not the probability that she doesn't laugh is 1 minus 0.72 or 0.28. And that's going to happen 1 time. So she's going to laugh at 6, not laugh at 1. That's where this equation comes from. So we're going to do 7 choose 6 to figure out the number of ways. Turns out there are 7 to choose 6 times the probability of her laughing, which is 0.72 raised to the 6th power, times the probability of her not laughing, which is 0.28. And that's going to be to the 1st power. You don't need to write that, but it is helpful to note when you're doing these, if you're finding for a specific value the probability, then the exponents of these are always going to add up to the total number of trials in 7. So we do 7 times 0.72 to the 6th times 0.28 to the 1st. And that will give you boy, look at that. That seems awful high. I'm going to check my numbers here. Oh, how do we enter this into the calculator? That's going to be in your catalog, and I think it's at InChooseR. Make sure you have that available. If that is not available, there is a formula for it, and I believe it looks like InChooseX is equal to n factorial divided by x factorial times n minus x factorial? I think that's right. I'm going to double check that. I think that's correct. R factorial. Yeah. Got it. Sweet. And that's going to give you this number 7. That'll be 7 factorial over 6 factorial times 1 factorial. 1 factorial is 1. 6 factorial will be 6, 5, 4, 3, 2, 1 are all going to cancel with what's in the numerator, and only a 7 will be left over. All right, I'm going to do this math one more time because my answer seems funky. 0.72 to the 6th. Oh, maybe not. Dang. All right, times 0.28 equals that times 7. Okay, so hey, look at that. Probability is equal to 0.273, which means there is a 27% chance that she laughs at 6 of my jokes. 27.3% chance that she laughs at 6 of my jokes if I have a 72% laugh rate with my wife. You guys, she's pretty easy. I'm not gonna lie, to make her laugh. Are you giggling over there? Quit giggling. What's the probability that Miss Lego laughs at 3 or less jokes? So that's going to be the probability that J is less than or equal to 3, and so that would be equal to the probability of J equals, it's probably, it is possible that I miss 7 times in a row and none of my jokes land. So it's the probability that none of my jokes land plus the probability that one of my jokes makes her laugh plus the probability that 2 of my jokes make her laugh plus the probability that 3 of my jokes make her laugh. Okay, so you would have to do this process 4 times and then add all those probabilities together. And you can do that, but it turns out there's an easier way because that's just much too long, okay? When you're finding just the probability of one of these individual values for a binomial distribution, you use binomial PDF, okay? So this one's binomial PDF because you're only finding 1. When you're finding a whole range from 0 to 3, you want to use binomial CDF, okay, and to get our values. And I'm not going to find the answers for these. I'll let you guys do those on your own, just to save some time because I don't want to have to run through all that. But practice and give it a shot and see if you get a reasonable value. If you get an answer that's bigger than 1, you've done something wrong, because if you find the probability of 0, 1, 2, 3, 4, 5, 6, and 7, you add them all together, you should probably get 1 is your answer, because that's every single possibility. What's the probability that she laughs at least 2 jokes and at most 5? Again, that's going to be binomial CDF. The probability that 2 is less than or equal to J is less than or equal to 5. So it would be 2, 3, 4, and 5 is what you do. And again, I would use binomial CDF for that. If it asks to show your work, this is the process that you do. You may need to use this thing here, but you can really just in your calculator do and choose R, and they don't need to see the jump from here to here to get that value. Calculate the mean and standard deviation of a binomial random variable. Sure. Okay, this is also on your cheat sheet. Binomial random variable has mean n times p and has standard deviation square root of n times p times 1 minus p. So let's just do that really fast. This is easy. The mean of our random variable j is equal to n times p, which is equal to, I'm telling 7 jokes, and the probability of success is 7.2 or 0.72. 0.72 times 7 is 5.04. So, and we're kind of measuring in the number of laughs that I get from Miss Slagle. So that's 5.04 laughs. Okay, so that's why we had kind of a high probability for p equals 6. It was relatively high, 0.27. So a high probability because it's kind of close to the mean, right? Okay, so that's the mean of our random variable j. How about the standard deviation of our random variable j? That is equal to the square root of n times p times 1 minus p, which is equal to the square root of 7 times 0.72 times 0.28, which gives you the value of the standard deviation of 1.19 laughs. Okay, so we can expect any given trial of 7 jokes to have a mean of 5.04, and we can expect any trial of 7 jokes to vary from that mean of 5.04 by about 1.19 laughs. I think I did everything. And again, I'm pulling those equations from this cheat sheet that you're given. Sweet. Okay, number 12. This one's pretty straightforward. The only difference between binomial and geometric, it's all the same checks. The difference here is it's binary, they have to be independent, they have to have the same probability on each trial, but you're doing it until you get your first success. Okay, you're going until you hit your first success. So what does that look like in terms of the joke problem? That would be find the probability that the first joke Mrs. Slagle laughs at is the 5th joke he tells. This is not binomial. You're going until you hit a success. This is geometric. So we'll call this random variable x. So x is equal to the joke I would say the first joke at which Miss Slagle laughs. Now here's what's crazy about a geometric random variable is there is a chance, so it basically looks like this. There's a 72% chance that she laughs and a 28% chance that she doesn't. Okay, well, if she laughed on the first joke, then x is equal to 1. Okay? Well, if she didn't laugh on the first joke, you got to tell another joke. And there's a 72% chance there and a 28% chance for failure. And so if x equals, so if she doesn't laugh at your first joke but laughs at the second joke, then x ends up being 2, okay? And so this continues. So x can take on a value. How many jokes could it take? In theory, she could never laugh at one of my jokes ever again, and that's quite plausible. That could happen. I didn't get her. Dang it.
Sorry, I was really focused on you.
Okay, 28%, and this could continue forever. So geometric, you don't know how many x can take on basically an infinite number of values. But with binomial, it's not possible. The number of basically laughs that can happen can be at most 7. So binomial is a little different. So it's this third letter. Remember, bin is the number is fixed, okay? And F stands for you're going until you hit your first success. Find the probability that the first joke Mr. Slagle laughs at is the fifth joke that he tells. Let's go to our chart. If x is a geometric distribution with parameter p, would be the probability of success. We already know is 0.72. So this is not j. I can't say j equals because j was a binomial random variable. This is calling x. Okay, it has mean 1 over p and standard deviation square root of 1 minus p over p. So you have those there if you need them. So we're looking for the probability that x equals 5. So that's going to look like this. So that means if x equals 5, she didn't laugh. So 1 minus p is the probability of failure. She didn't laugh at 4 of my jokes and then laughed at the 5th joke. So it's going to be 5 minus 1 is 4, and then that to the first power. So it looks like this. The probability that x equals 5 is a geometric variable is going to be 0.28 probability of failure to the 4th times 0.72. And if you have to show your work there, you might say, with parameter p equal to 0.72, that's 1 minus 0.72 to the 5 minus 1 times 0.72. And you get 0.00445. So the probability that the first joke she laughs at is my 5th joke. There's only a 0.4% chance. She's probably going to laugh at something earlier, basically. It's more likely. So think about it. Like, on what's the probability she laughs at the first joke? Well, that's 72%. So every successive joke that I tell, the probability of making it to that position gets harder and harder and harder and harder, but it is possible. So to get to the 5th joke, the probability of her laughing at the 5th joke and me failing 4 times in a row is less than 1%. And that should make sense. Okay, that's all I've got for you for this video. It was just a measly 4.5-hour video. Thanks for watching, and we'll see you at the next one later.